Some of the tallest skyscrapers on Earth are slowly sinking into the ground right now. Their enormous weight pushes down through the foundation, squeezing the layers buried underneath. Millimeter by millimeter, the entire building moves lower. Even the tallest skyscraper in the world, Burj Khalifa, also has this problem. In fact, it starts sinking right away during its construction, and its engineers had to calculate how far it would move before the first floor went up. But the sinking of skyscraper itself isn't something that scares engineers. It's something else, and which is literally a nightmare for engineers and residents together. So what exactly is hidden beneath these towers, and why can even the best engineered skyscrapers actually sink? Well, to understand that, we have to follow the weight from the top of the building all the way underground. Every time crews add another floor, the skyscraper gets heavier. The central core and columns collect that weight and carry it into the foundation. From there, the pressure enters the ground. But the ground doesn't behave like one solid block. Loose sand packs tighter under the weight. Deeper layers of weak rock can deform too. If the tower sits over clay, the pressure slowly pushes water out through microscopic gaps, so movement can continue for years. As those layers compress, the foundation moves down with them. Engineers call that settlement. If the whole base drops by roughly the same amount, the tower can remain level. Trouble begins when the ground beneath one section compresses more. Engineers call that differential settlement, and it can slowly pull the entire skyscraper off level. That was exactly the risk engineers faced in Dubai in 2003, before the Burj Khalifa had its first floor. Back then, the project still carried the name Burj Dubai. Hired Hayter Consulting to investigate the site in downtown Dubai. Between June 1st and July 23rd, crews drilled 23 boreholes. Later, drilling reached 140 meters underground. The cores didn't find one hard, uniform layer of bedrock. Crews pulled up marine deposits along with weak calcareous sandstone and calci-siltite. Some sections resisted pressure better than others, but overall, they didn't find anything solid. Workers then expanded pressure probes against the borehole walls and sent seismic waves between deeper holes. Piezometers tracked the groundwater moving through the site. By October 2003, engineers had a map showing where the ground might compress more once the tower's weight arrived. Now they needed a base that could spread that weight without allowing one section to move ahead of the rest. The first part of that solution was a huge concrete slab shaped around the tower's footprint. At ground level, the Burj Khalifa's 3 wings spread out from the central core in a Y shape. The walls and columns carry their weight into a reinforced concrete slab that's 3.7 meters thick. Engineers call it a raft. Each wing stretches roughly 50 meters from the center, and the complete raft covers almost 3,305 square meters. That's nearly half the area of a standard football pitch. The wide base spreads the pressure across much more ground. Its thickness also allows it to bridge slightly softer areas underneath. If the soil below one wing gives a little more, the concrete raft transfers some of that load towards stronger areas. This keeps the 3 wings working as one foundation. But the raft still needed something deeper to stop all that weight from pushing it too far down. That deeper support came from 192 concrete piles hidden beneath the raft. Each one measures 1.5 meters across and reaches roughly 47.5 meters below the concrete base. That's about the height of a 15-story building, only buried underground. Crews drilled each shaft through Dubai's weak carbonate rock. Water could enter the open hole and make its sides collapse, so workers filled it with a thick polymer drilling fluid. The fluid pushed against the walls and held the shaft open. Next, a crane lowered a long steel reinforcement cage into the hole. Crews then fed self-compacting concrete through a pipe reaching the bottom. As the concrete rose, it pushed the drilling fluid back towards the surface. These piles didn't rest on a hard shelf of bedrock. The surrounding rock gripped their sides as the tower pressed downward. Engineers call this shaft friction, and it carried most of the load. The pile tips added some support, while the raft still pressed directly against the ground above. But installing 192 piles didn't automatically guarantee even movement. Engineers needed to know how each one would behave under the finished base. Before completing the foundation, they tested 7 full-sized trial piles. Hydraulic jacks pushed some of them with forces reaching 64 meganewtons, roughly equal to the weight of 6,500 tons. Strain gauges placed at different depths showed where each pile transferred its load into the rock. Engineers fed those results into computer models, including a finite element program called Abacus. The model showed how the piles would interact through the surrounding ground, almost like a group of connected springs. That allowed the team to arrange the piles around the Burj's Y-shaped footprint and balance the support beneath each wing. The stiff raft and concrete tower above helped spread any small difference that remained. Now the weight had a controlled path underground. Then Dubai's wind began shifting that pressure from one side of the foundation to the other. At 828 meters tall, the Burj Khalifa works like an enormous lever. When a strong gust pushes the upper floors, the force travels all the way down to the foundation. One side of the raft presses harder into the ground while the opposite side releases some pressure. As the wind changes direction, the loads inside the piles keep rising and falling. Over time, those cycles could weaken the friction gripping their sides. So SOM and wind consultants from WRDI shaped the tower to reduce that force before it reached the base. Each wing supports the other two through a 6-sided central core. Higher up, the floor plate changes at every setback. This breaks apart the regular wind vortices that could otherwise push the tower in a steady rhythm. The foundation team calculated that wind would change individual pile loads by less than 10 meganewtons in either direction. Their tests showed that those cycles wouldn't seriously weaken the shaft friction. But the piles also faced a slower problem underground. Dubai's groundwater contains aggressive chlorides and sulfates. If it reached the steel reinforcement, rust could expand inside the concrete and crack the pile from within. Engineers used dense, low-permeability concrete with corrosion inhibitors. Extra concrete covered the steel, while waterproofing protected the raft. They also placed a titanium mesh anode beneath the foundation and connected it to an impressed current cathodic protection system. A controlled electric current keeps the reinforcement cathodic, which slows the chemical reaction that causes corrosion. That protection helps the raft and piles keep the same strength they need to share the tower's weight evenly. And the measurements show how closely the complete system followed the original plan. During the design stage, engineers calculated that the Burj Khalifa's foundation could settle by roughly 45 to 62 millimeters. On February 18, 2008, crews had placed close to 80% of the tower's expected load. Settlement markers recorded a maximum movement of 43 millimeters. Across another part of the raft, they measured around 29. That left a difference of about 14 millimeters across a base wider than 80 meters. A later assessment suggested that the foundation moved by only another 1 or 2 millimeters before the Burj Khalifa opened on January 4, 2010. So the tower didn't move downward by exactly the same amount everywhere. The difference simply stayed small enough to keep its 3 wings level. But deep piles aren't the only way engineers control this movement. In Miami, crews working on the Waldorf Astoria hotel and residences faced porous limestone mixed with layers of sand. They used a method called deep soil mixing. A drilling rig pushes a mixing head about 40 feet underground. The blades can cut a circle roughly 9 to 10 feet wide while injecting cement into the existing soil. Once that mixture hardens, it becomes soilcrete. Crews overlap those circular sections to form a stiff underground grid. The grid carries more pressure and also limits groundwater entering the excavation. Even with systems like these, some towers can keep moving far longer than engineers expected. San Francisco's 58-story Millennium Tower opened in 2009. Its 942 original piles reached between 75 and 85 feet into a layer called Colma sand. Much deeper down, a layer of old bay clay continued compressing. By 2019, the tower's northwest corner had settled 17.3 inches. Because that corner moved farther, the top leaned about 15.5 inches towards Mission and Fremont Streets. Researchers found a different pattern along Florida's coastline. Between 2016 and 2023, Sentinel-1 satellites tracked 35 buildings from Miami Beach to Sunny Isles Beach. The structures moved downward roughly 2 to 8 centimeters. The University of Miami team linked much of that movement to construction activity and compression in sandy layers of limestone, although researchers still need longer monitoring to confirm what's happening beneath each building. New York shows how sinking can spread beyond a single foundation. In 2023, the U.S. Geological Survey estimated that the city's buildings weigh around 762 million tons. Satellite measurements show New York moving down by roughly 1 to 2 millimeters each year on average. Building weight plays a part, while softer ground and natural geological movement also contribute. Engineers call that wider movement land subsidence. An entire area can descend together, while differential settlement develops when one section of a foundation moves farther than another. Every skyscraper foundation has a calculated movement limit. Engineers design everything underground around that number. The building can then settle slightly and remain level. And that's why even the best engineered skyscrapers can actually sink. So yeah, a few millimeters of sinking can actually sit right inside the original plan. The real challenge is keeping the entire tower perfectly level while it happens. If this kind of hidden engineering is your thing, hit follow. We'll keep covering more insane architecture and some of the biggest mega builds on Earth.